an equilibrium point, say for a two-dimensional system, will be stable if, well, one of two things happens. Well, okay, typically. It's either a sink, maybe a real sink, maybe a spiral sink, or it's a center. Now I'm drawing these ovals here a little wobbly on purpose, because maybe it's a non-linear system. You know, you wouldn't get wobbly ovals with linear systems. Maybe it's a non-linear system where you've got periodic solutions near an equilibrium point that are a little wobbly. That can happen technically. These would be examples of stable equilibrium points. The first two, these two, are also called asymptotically stable. Okay, not only are they stable, but they're asymptotically stable. What does this mean intuitively? It means if you perturb the system a little bit, change the initial condition a little bit, it's basically still the same behavior in the long run. That's the intuitive idea. Bring this up with a pendulum physical model, right? The downward equilibrium, the point straight downward equilibrium is stable and also asymptotically stable if you've got friction. Because even if you give that pendulum a little flick, as long as the flick is small enough and doesn't cause it to go around the horn, it's going to stay near where it started and still get decay to zero. On the other hand, sources, whether they are real sources or spiral sources, and also saddle points are unstable equilibrium points. Because if you flick them, the solution moves away. Like pendulum pointing straight upward. If you could get a pendulum to point exactly straight upward somehow, it would stay there forever, right? If it was a rigid rod. No perturbations. Of course, in real life, there are perturbations. Just even the slightest amount of wind will start it falling, okay? That's unstable. Flick it a little bit, even a tiny bit. Some oxygen molecule hits it in a vacuum. One oxygen molecule hits it. It's going to fall over. It's going to be unstable. That's physically important because stable equilibrium points are the observable ones. Unstable ones are not really observable in physical systems, right? You're not going to see a pendulum standing straight up unless somebody's holding it, right? That's not allowed. These are the observable equilibrium points. These are the not observable ones, but they exist mathematically, and they're still important mathematically for describing the system and other solutions.